Recording in progress.
Hey kids, Smath here. Wanted to talk to you about net ionic equations today. This is a topic that's given students previously a lot of difficulty because it's a pretty complex topic. There's a lot of moving pieces. So let's start out with a couple of definitions first. A net ionic equation is listed above here. It's an equation that contains only the substances directly involved in the reaction. So if they're involved in the reaction, we've got to look at states of matter because by involved in the reaction, what we're talking about is, did they change state? Did they go from a solid to an aqueous? Did they backwards, vice versa? So how did they change? So we're looking at that. All right. This does not contain things called spectator ions. Spectator ions are a vocab word that you all wrote down. These are ions that do not participate. So what did they do? They merely brought the other ions to the party. So these are going to be ions that are on both sides of the equation. As the name implies, and I say this all the time, spectator ions are always going to be aqueous. So this NO3 is going to be AQ. All right? It's got to be spectator ions. So that being said, all ions in any reaction are going to be considered aqueous no matter what, not just the spectators, but anything that's ionic. That's going to come into play. So for synthesis, decomp, and combustion, for those three, the molecular equation and the net ionic equation are the same. We just have to look at what are the states of matter that we're dealing with. The net ionics that we're dealing with really have a larger effect in single replacement and double replacement. And we're going to go through examples of each one of these. So when we look at states of matter and reactions, this is a very general rule of thumb, but we're going to use the periodic table here to be careful. Use the periodic table. And if we have a solid and a gas, we're probably going to end up with a solid. Now, you'll always be given the reactants, so you don't have to figure those out. The ones that I'm asking you to determine and to think about are the products. So if you mix a gas and a gas, we're probably going to have a gas. If you mix a solid and an aqueous, you're probably going to end up with an aqueous and a solid. And and it goes with saying this looks like it's going to be a synthesis reaction. This looks like it's going to be a synthesis reaction. This looks like it's going to be a single replacement reaction. And this last one looks like it's going to be a double replacement reaction. Pardon me, let me get this back and give me my screen back. There we go. So this last one probably going to be a double replacement. Now, let's start with synthesis. Notice we're doing these with elements. Very simple. Element, 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 element. This goes again. I've been saying this since we started this unit. Please watch your diatomics. So your N2s, your O2s, your H2s, please watch those. We don't want to see any single oxygens. No regular chlorines. No atomic. Now this last one, so if I take N2, O2, I combine those together. At this point, we've got to look for, watch the charges. Okay. So I've got a charge up here of, in this case, -2. And nitrogen we're going with is going to have a charge of 3. That's just its normal. So we're going to go 3, we're going to go 2, and we're going to crisscross those and get N2O3. Now, this is really weird for us. We're not used to seeing nitrogen go positive, but it does have the ability to do that because of its electron configuration. So rather than looking at the signs of the charges, let's just look at the magnitude, the size of that charge. And so as we look at the second one, I've got sodium and chlorine going together. Keep in mind, these do not have charges over on the reactant side. Those are elements. Elements don't have charges. Then when I put them over on the product side, now I come in, I go +1, -1. That's balanced as written. Nice formula. But in order to balance this formula now, because I have two chlorines over here on the left, I have to come back and put two chlorines on the right, which changes my sodium. Let's bring it back and put two chlorines there for that sodium to work. Now we've got a nice balanced, and we're going to clean up those charges. Get rid of those. Let's look at our next one. We're going to make a little bit of water, hydrogen and oxygen. Okay, take hydrogen gas. Now, both of these, diatomics, watch those. Hydrogen's a gas, oxygen's a gas. We're being told this. When we combine these together, we're going to get H2O, and we're getting H2O because that charge is +1, -2. When we crisscross, we bring that down. That changes my hydrogens, or my oxygens are 1. I've got to have another oxygen. So I put a 2 up front. That changes my hydrogen to 4, so I put a 2 there. Now, state of matter, I'm going to get rid of those charges. State of matter, I said earlier, well, we've got a gas, and that should make a gas. And this probably is a lot of the time. We're saying, well, yeah, but H2O is water. That's a liquid. I would take that as an answer. I'm just trying to stick with the usually the guidelines that I gave you earlier, that a gas and a gas would form a gas. So I'm not wanting to confuse you with states of matter. Now, let's look at this last one. We've got two solids. This one's kind of an interesting scenario, but it shouldn't be confusing. Solid, solid is going to make a solid. The only time we're using liquid is when we're dealing with water. Okay? So solid, solid make a solid, and this one balances out quite nicely formula-wise because magnesium's +2, sulfur is -2, and we like that. Okay? Last one or the second one for this, last one for this video. I'm going to make two videos for you. Decomposition. Now we're breaking things apart and we're having to look on the periodic table for some states of matter. Keep in mind, solids are over to the left, gases are over to the right. So when I take this copper chloride apart, it's got to be decomp. I only have one reactant. That's going to split into copper. That's going to split into chlorine. And look, there's my diatomic again. Okay. We know that copper is a metal. We used it in our lab last week. So we know that's a metal. That's a solid. And the chlorine is going to be a gas. It's over on the right-hand side of the table. Okay. With that chlorine being diatomic, I have to come back and put a 2 in front and a 2 in front to get my copper to balance. Okay. That was a transition metal one. Here's a non-transition metal, strontium, and fluorine is a solid. And when we go to break that apart, strontium forms, fluorine forms. Fluorine is diatomic, and so this 2 is here because it's diatomic. It's an element by itself. This 2 is here. We were given that, but that 2 is there because strontium was +2. Don't transfer those subscripts. Just watch your diatomics. So we've gone from a transition metal, a light metal over on the left-hand side, and now here's another transition metal. We've got iron. Iron nitride, we have a solid, breaks apart. Again, a solid and a gas. These are very common for decomposition for at our level. So be looking for that with decompositions. With this one, though, I wanted to make sure we saw that nitrogen is breaking apart. That too is there because of diatomics. Okay, diatomic. That too is there because Fe is 2 plus. And of course, this 3, we have plus 2, minus 3. So the 3 came down, formed that. Now I've got 3 irons, and I balance it out with 3 irons. Okay, so that's synthesis and decomp. And we have those two straightened out to keep things easy and keep things short. That's where I'm going to stop this video. And then I'm going to pick up and I'm going to do another one with single replacement, double replacement, and combustion. I'm Smath, and I hope this video helps you.